So a pleasant day to everyone. Today we're going to discuss part 2 of Module 2 for the subject CE411, which is horizontal alignment. So in our previous discussion, we have introduced what is the importance of horizontal alignment, and we have also discussed as well the first type of horizontal curve in which we apply the alignment. So in here, we'll be discussing the other curves that we apply in our road, which is the compound curve. So as a review, we have compound curves are basically two curves that are connected at a common point and they are facing the same side. So they could have or they will have different radii. Because if they will have equal radii, then the two curves will simply be a simple curve. Okay? So for compound curves, our elements would now consist of our R1 and R2. We have your PC, or the point of curvature, or the start of our curve. Then we have your PT, which is the point of tangency. Then we have your PCC, which is the point of compound curve. We have your PI, which is the point of intersections of our T1 and T2, which are the tangent lengths of curve 1 and curve 2 respectively. Then we also have our common tangent, which passes through our PCC. And the tangent now passing our PCC, or the common tangent, will simply be equal to the sum of your T1 and T2. Then we have your V1 and V2, which is the vertex of curve 1 and curve 2, or the intersections between T1 and the common tangent, and the intersection of T2 and the common tangent, respectively. You also have your I1 and I2, or the central angles for the two curves, 1 and 2, or this could also be called your delta 1 and delta 2. Then we have your I, which is the angle of intersections of our tangent, which is simply the intersection, or the angle of intersection 1 plus angle of intersection 2. Then we have our L1, L2, which is the arc length, or the curve length of curve 1, and the arc length, or length of curve 2. Then, lastly, we have our LC1, or the chord length of curve 1, and LC2, which is the chord length of curve 2. And lastly, we have our LC, or the length of chord of the compound curve, which is simply measured from PC to P. Okay? So your internal angles, I1 and I2, aside from being taken between the two radii, the radii of the curves is also equivalent to the angle formed between your common tangents and your tangent length. So for compound curves, the approach will be the same as the approach for simple curves, except that we are analyzing now two separate simple curves. So if we have here our compound curve, so what we will do here is to simply take note of your chord lengths for the curve, for the first curve and the second curve. And then we determine now our mid coordinate, okay, or our middle coordinate. So the shaded portion now will be the portion in which we have to clear our road so that when vehicles traveling from curve 1, so this section, once they arrive here, they will be able to see now our obstructions. So dapat walang obstruction dito, same as for your simple curves, so that we will have a safe maneuver of vehicles. Okay. So next type of curve, we have your reverse curve. So the third type. So the reverse curve is also composed of two curves that could have equal or unequal radii, and they are facing opposite sides of our road section. So the elements for the reverse curve will consist of our R1 and R2. We have your point of curvature, PC, which is the start of our curve. Next, we have your PT, or the point of tangency. Then we have your PRC, or the point of reverse curvature, the point wherein the two curves will meet. And then we have T1 and T2, which is the length of our tangents for curve 1 and curve 2 respectively. So we have here T1 and T2. And then we have our common tangent, which will be passing through our point of reverse curvature, which is also equal to the sum of T1 and T2. Then we also have our V1 and V2, which is simply the intersection of the common tangent, and your tangents, V1, V2. Then we also have I1, I2, which are the central angles of curve 1 and curve 2. Then we have our length of curves, or the arc length, curve 1 and curve 2. L1 is curve, L2 curve length. Then we also have LC1, LC2, which is the chord length, so the linear distance between PC and PRC, LC1, and linear distance between PRC and PT is LC2. Then we also have, for the length of the common tangents, that's equal to T1 plus T2, as I have said. So that's V1 to V2. So for reverse curves, we have two types. And for reverse curves, this is usually unadvisable for high-speed roads because our super elevation on the reversal point, at this point sa PRC, will be or cannot be provided. So mahirap siyang gawin. Kaya usually, pag high speed yung road natin, ang makikita natin would usually be tangents and curves instead of reverse curves. So simple curves or compound curves. Kasi hindi naman, pag high speed roads, hindi natin ina-expect na merong change in direction. So pag high speed, usually straight lang yan o kaya isang direction yung pinupuntahan niya. It's either to the left or to the right. Okay? So for the two types of reverse curve, we have here your parallel tangents. So reverse curves with parallel tangents. And then we also have non-parallel tangents. So this will now apply for non-critical speeds. Okay? So low speed roads. Okay? So the analysis now for reverse curve will be somewhat different with our analysis for simple curves and compound curves. So in that case, let us solve an example for reverse curves. So let's say we have here a reverse curve. So we have now to determine the flattest common radius for the given reverse curve. So when we say common radius, it's an equal value of the radii. So that can be inserted between the parallel tangents. We have AB and BE. So between parallel tangents that are 25 meters apart. So we have here PE, or P will be the distance between your parallel tangents without exceeding 250 meters for A, or the distance between horizontal, the linear distance between A and D or A and B. Okay? So distance between the 2 radius. So basically, kung parallel yung tangents natin, yung radius din natin will be parallel. Okay, so what's the distance between the two? Radii will be 250. Okay, so for this kind of reverse curve, so this is a reverse curve with parallel tangents. So for this kind of curve, our analysis now from the figure is that we have for T that is simply equal to AE plus FB, wherein AE now is computed as R1 times 1 minus cosine of the central angle, and then FB is equal to R2 times 1 minus cosine of the central angle of the curve. Or simply, P1 now, or P is equal to R1 plus R2 times 1 minus cosine of your central angle. And also, for AD, it's equal to EC plus CF, in which EC now is equal to R1 sine of theta and CF is equal to R2 sine of the central angle delta. So, completing this, AD is simply equal to R1 plus R2 times sine of the central angle. Okay, so using these equations now, we can now solve example number 2. So, from the equations that we have just shown in the previous slide, we can now solve example number 2. So, for our solution, we have P, which is equal to 25 meters. So, we could write that as R1 plus R2 minus or times 1 minus cosine of the central angle. And since R1 and R2 should be in equal value, we could simplify this as 2R times 1 minus cosine delta. So we have already P. So one equation, we have two unknowns, so we need one more. So next equation will be taken from AD. So AD now is equal to 250 meters. And from the equations we just have mentioned, AD is equal to R1 plus R2 times sine of theta. R1 is equal to R2, so we could rewrite this as 250 equal to 2R sine of theta. So we now have two equations, two unknowns. 2R can be eliminated, so that we can solve for delta. So with that, we have now 25 equal to 2R times 1 minus cosine delta all over 250 equal to 2R sine of delta. So 2R cancels out. Okay. So we could simplify this as 25 or 0.1 equal to 1 minus cosine delta over sine delta. From identities, 1 minus cosine delta divided by sine delta is equal to tangent of delta over 2. So from here, we'll be able to get now the value of delta, which is equal to 11.42 degrees. And from the value of delta, we can now solve for the value of R using either of the two equations. So R now is equal to 631.314 meters. Okay? So ganun lang siya. As long as you know the equations, you can solve your problem. So for the other type of reverse curve, which is the non-tangent or non-parallel reverse curves, the analysis or the approach will be the same as for compound curves. So we'll just analyze it as two separate simple curves. So we determine the chord length of each curve, and from there we'll be able to identify now our coordinates, middle, and our external coordinates. And from here, we'll be able to identify now our area in which it should not be obstructed to have a clear view of the opposite lane. So aside from the three types of horizontal curves that we just have discussed, which are your simple curves, compound curves, and reverse curves, we also have what we call your broken back curve. So what are these horizontal curves? So broken back curve would be characterized by a short tangent that is placed between two curves that are facing or moving in the same direction. Okay? So usually broken back curves would be avoided as much as possible in our design since most drivers would not expect succeeding curves to be in the same direction. Okay? So okay lang kung curve and then another curve yung same direction ng movement natin. Pero usually sa drivers, they would not expect having a curve and then a straight line and then another curve in your road section or in your highways. So usually this is avoided in highway designs. So this will what a broken back curve would look like. So we have here an initial curve, and then after that curve you have inserted a tangent line or straight line and then connected another curve. So this is usually avoided. So if this happens to be in existing in a road section or in a highway, usually you have to redesign this so that this broken back curve would simply be a compound curve. Okay? So to understand or to have an idea of what we do for horizontal alignment when there is a broken back curve in our design, let us have an example. Okay? So let's say the broken back curve shown is to be replaced by compound curve whose ratio between the radii is R2 equal to 1.8 R1. So the ratio is 1.8. So determine now the new values of the radii and the new values of the tangent of the compound curve that we have to replace or that we are going to replace for the given broken back curve. So initially, we have our first curve with tangent equal to 250. We have our central angle at 30 degrees. And then we have a very short tangent at 45 meters. And then another curve connected to the end of the tangent with tangent 350 meters and central angle 20 degrees. So for this problem, what are our given? We are given now the tangent of the first curve at 250 meters, tangent of the second curve at 350 meters, the short tangent at 45 meters, and then what we are looking for is the new radii, and we're given the relation of the radii as 1.8 of R1 equal to R2. So to solve this one, so the broken back curve, we want this to become a simple or a compound curve. Okay, so we are going to remove the 45 meter here. So ano nang magiging radius natin para makover pa rin yung point na ito, same point to this point, but we have to use a different radius of curvature for our curves. Okay? So with this, we now have our tangent. Okay? So this line now will be the tangent of the curve. Okay? So next, we have our common tangent. Then we have here our tangent 2 of the next curve. So basically, this line now is our tangent of the first curve, but this is T1. So let's call this T sub A. Then 350 here is T2. So let's call this line instead as T sub B. Okay. So this is now the meet up point or the point of common curve, TCC. Okay, so this one is also TA. This one is also T sub B. So for our solution, we now have our first curve. So this is R1. This is R1. This is also R2 and R2. So what we will be doing is to solve this figure now as a compound curve. Okay? But before that, we know that the distance between the vertices of our compound curve and the vertex of the broken back curve will be equal. Okay? So in that case, we now write T1 plus our short tangent plus T2 is now equal to TA plus TB. Okay? And then this substitute now our values. So we get T1 is 250, ST is 45, 350. So this is now equal to 645 meters. That's equal to TA plus TB. So this one now is our first equation. So next, from our figure or from compound curves, okay, so from the vertex, if I will put now a line here, so we have now your tangent radius, and then we have this angle as theta over 2, or this is delta over 2, and this is for the first curve. Okay? So we could write now by tangent, we could write now that the tangent of delta divided by 2, so this is 30 divided by 2, so tangent of 15 is equal to opposite over adjacent tangent of E divided by R1. And at the same time, we're going to draw now a line here. This is now tangent of 20 divided by 2, so 10 is equal to tangent of 10 is equal to TB divided by R2. Okay? So with that, we could rewrite now our equation as TA is equal to R1 tangent of 15, and we have TB is equal to R2 tangent of 10 degrees. So take note that we have the relationship between R2 and R1. R2 is equal to 1.8 R1. So substitute R2 with this value. So we get now TB equal to 1.8 R1 tangent of 10. Okay? So since we now have TB and TA in terms of R1, so two unknowns na lang. So TA and T1. So we could substitute now TA and TB in the first equation. So that is now written as 645 meters. That's equal to TA is R1 tangent of 15 plus 1.8 R1 tangent of 10. So one unknown, we can now solve for the value of R1. So R1 now is equal to a value of 1,101.928 meters. So multiply this by 1.8, we get R2, which is equal to 1,983.470 meters. And then, substituting R1 and R2 in TA and TB equations, we also get TA equal now to 295.261 meters. And we also have TB, which is equal to 349.739 meters. So these are now the new property of our compound curve if we want to remove our short tangent in our broken back curve. Okay, so that's it for the second part of horizontal alignment, which is the application of horizontal alignments for compound curves, reverse curves, and broken back. So thank you for listening. So for your references, we have the books of Ricardo Sigua, the lecture notes of Engineer de Guzman, and then we have the following websites for you to read aside from this.